And now we're moving on to Chapter 10, which is all about exponential and logarithmic functions. And as you can see, 10.1 is all about exponential functions. So an example of an exponential function is what we have right here, this y equals 2x. Now notice, it's very different from y equals x to the 2. That's a specific quadratic function. Quadratic means our base is x, so our base is our variable, and it's to a specific power, 2. When that power is 2, then it's a quadratic. If that power happened to be 3, it would be called a quartic, or should I say cubic, sorry, cubic. If that power was 4, then it would be a quartic equation. These ones are called exponential specifically because it's y equals something, like in this case 2, to a variable x. So our variable x is the exponent. That's what makes it an exponential function. So let's see what this one, that y equals 2x, looks like if we were to graph it out. So if we have, we'll just plug in some values. When x is negative 3, remember that negative value means we're going to flip it to the reciprocal. So 2 to the third power is 8, but because it's negative 3, we have to flip it. Instead of 8 over 1, it's 1 over 8. Do the same thing with negative 2. 2 to the 2 is 4, but because it's negative, we flip it. So instead of 4 to 1, it's 1 over 4, and 1 over 2. 1 over 1. Well, actually, anything to the 0th power is just 1, so we'll just say it's 1. Whenever we have 1/2, remember that means take the square root of it. So 2 to the 1/2 power is just the square root of 2. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. Now we just plug some of those values in. When x is negative 3, here we are at 1/8. Very, very short value, very small. Move up ever so slightly at negative 2 1/4, a little bit more at negative 1 1/2, even more so here at negative, or not negative, at 0, positive 1. Then at 1/2 here, we're at square root of 2. So moving up a little bit more. Then at 1 we're at 2, 2 we're at 4, 3 we're at 8 way up here. And we also even included this one here, the square root of 7. We just put that in there for kicks. 2 to the square root of 7 is approximately 6.3. So you can see over time it slowly moves up, but it continues to move up faster from each dot that it goes to. So down here, it looked like it would have been going like this. But by the time we're here, it actually looks like it's going like this. But over time, it isn't any of those straight lines. It is a perfect curved line that continues to move upward. So that would be an exponential function. So in general, an exponential function will have the form y equals a times b to the power of x. Now that a is our initial value. So it's just our starting point. So we would say if we started with 4 of something, let's actually draw that out. 4 of something, and it doubled each time. So this one here, the b value, I'm just going to call that our growth value, how much we're growing by. So if it doubles each time, and we're starting with 4, so initially our x is 0, and so our y is 4. So the next time we go around, x is 1, and it all doubles. 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 of what we had before. So now all of a sudden our y equals 8. Now if we were to go again, x to the 2, our second time around, we would just take whatever we had here and double it again. So in total, it looks like we now have y equals 16. So again, you can take your growth value, like you're doubling it, or you're halving it, or you're timesing it by 3. That's your b value right here, times your initial value where you started, and then just however many times you're doing it. That's essentially what's happening during an exponential function. So things about exponential functions, they're continuous and they're one-to-one. By continuous, we mean that there's never really a break in them. So if we had our graph here, it continuously moves. If we had one of those step functions, those break. those move like this. And they technically are not continuous because you can visually see there's a huge chunk missing. So those ones would not be considered a continuous function. But our exponential function is continuous, and it's one-to-one because just like we can check a function, whether it is a function or not, by doing a vertical line test, we can do a horizontal line test to check if it's one-to-one. And all exponential functions pass this, so they are one-to-one. The domain is the set of all real numbers, and what that means is x, the domain, we can plug in anything we want. It doesn't matter what number. You can plug in -100, you can plug in 100, and they will always give you a number. The x-axis is an asymptote of the graph. Again, let's see what the graph looks like. We go like this. Notice how it'll come very, very close to the x-axis here, but it never actually touches it. It'll get down closer and closer and smaller and smaller and smaller as we go, but it never actually touches it, so it'll always be an asymptote at that x-axis. The range is the set of all positive numbers if a is greater than 0, and so that means if our a is greater than 0, the range is everything up here. In this case, though, if we had the graph where a is less than 0, it would look something like this as it grows. And so our range is all of these negative numbers down here. So that's what the range means. The range of all positive numbers if a is greater than 0, all negative numbers if a is less than 0. That's all that one is saying. Oops. The graph contains the point 0a, that is the y-intercept is a, so wherever your initial value is, like in this case, that's our initial value right there. We always start right on our y-axis and move from there. The graphs of a, or of y equals a b to the x and y equals a 1 over b to the x are reflections across the y-axis. Now again, just an example of what that looks like or what that's getting at. If we were to draw the graph here, if this one here was our first one, the y equals a b to the x, then y equals a 1 over b to the x would be a perfect reflection of it over the y-axis. Again, notice our y-axis right here, use it like a mirror. They'll perfectly flip over and look just like the other one. That's how that works. So there are two types of exponential functions. One is exponential growth. It looks like this. Over time, you can tell it is getting bigger. It is growing. Exponential growth, exponential decay, as you can tell over time, it's getting smaller. Growth and decay. So if we have a is greater than 0 on both of them, our initial value is greater than 0. If b, our growth or our base, is greater than 1, then it's going to be exponential growth. It'll be getting bigger over time. If that b value, our growth or our base, is in between 0 and 1, then it's getting smaller over time. And it looks like an exponential decay, which makes sense if you think about it. If we had y equals, let's say our initial value was 1, and our growth or our base was 1/2 to the x, it's growing by 1/2. That means it's getting smaller. You're cutting it in half each time. If I had 16 was my initial, then I cut it in half, down to 8, down to 4, down to 2, down to 1. It's just getting smaller over time. That's exponential decay. That's how that works. So if we wanted to determine whether or not we have growth or decay, if we have y equals 1/5 to the x, well again, our base or our growth is 1/5, which is in between 0 and 1, so we know it's decay. Let's try the next one. If we have y equals 3 times 4 to the x, we really don't care too much about that 3. That's the initial value. We're just looking at 4, which is our growth, so it's getting 4 times as big each time, which means it's growing for sure. And the last one, if y equals 7 times 1.2x. Again, we don't care about the initial value. We just want to know how much it's growing by, and it's getting bigger by 1.2, which is greater than 1. So it is actually growing over time. That is an exponential growth then. So remember, exponential functions are frequently used to model growth or decay of a population. Again, one good example of that is a lot of times they'll use it to talk about bacteria growth in biology. You can start off with one little bacteria, and then he would double, so all of a sudden we have 2, and then they would double, so the next time we have 4, they would double, now all of a sudden we have 8 little bacterias, they would double, now all of a sudden we have 16 bacterias, and so on. Exponential growth.